lecture for today. I have Daniel Kuhn. Daniel is a professor at EPFL in Lausanne. He got his Master of Science from ETH in Zurich in theoretical physics. Then he moved to St. Gallen for a PhD in economics. And before becoming professor at EPFL, he also was in the US as a postdoc at Stanford. Then he moved to Imperial College as a faculty member there for 5-6 years before joining EPFL in 2015. So we're very much looking forward to having you here. Thank you.
Thanks a lot, Spiros, for the nice introduction, and I'd like to thank all the organizers for inviting me here. It's a great workshop, and it's a great pleasure to be here. So my talk will be about data-driven optimization, and I'll first start by motivating why I'm doing what I'm doing, and hopefully towards the middle of the talk, I will switch to chalk talk style lecture where I do some real derivations and show you how things are really done. But you shouldn't be afraid of that, because the only thing I'm assuming you to know in order to follow that chalk talk is basically linear programming. That's one thing. And the other thing, you should know what a norm is. Okay? So two things. But I think most of you know linear programming and know what the norm is. So these are the requirements. Okay? Of course, we're going to use these things in a sophisticated way, but you should always keep in mind it's at the bottom of it, it's very basic. Okay. So what I would like to discuss today is stochastic programming problems of a very simple kind. So these are one-stage stochastic programs. You pick today a decision x in some feasible set script x, and the goal is to minimize some expected cost. So we have a cost function or loss function L that depends on your decision, and it also depends on a vector of uncertain problem parameters xi. And the expectation is, of course, taken with respect to the distribution P of xi. Okay? So that's a one-stage stochastic program. It's the simplest stochastic program you can think of. And for later reference, I'm going to refer to J star as the optimal value, so the minimum of that problem. And I'm going to denote by X star an optimal solution. For simplicity, let's assume that this is unique. So this is a very simple stochastic program, yet it has already quite a number of fundamental applications. For example, the famous news vendor problem in supply chain management, it's really the basic model of inventory theory, is of that form. In finance, if you would like to, say, find a portfolio that minimizes an expected disutility or maximizes expected utility, you can also bring the problem exactly to that form. Very topical in machine learning, most classification and regression problems can also be formulated in this way. I didn't specifically mention energy problems. It's clear that many energy problems can also be formulated in this way. However, energy problems are often dynamic, and I would like to not touch the problem of dynamic problems today, because this problem is already hard for me. Okay, so let's keep it simple. But of course, you can apply these techniques directly to energy problems, and maybe we can discuss a bit later how you would do that if the problem is dynamic. But for the moment, let's look at that problem. Okay, so even though this problem is simple, it's a one-stage problem, static, and has a number of important applications, it still suffers from two fundamental shortcomings. Okay? So the first one is that even in very simple settings, this problem is computationally hard. It's intractable. So here is an example. Let's assume that our decision x is a vector of different production quantities for a bunch of different products. And the vector xi of uncertain problem parameters is just the vector of unit production costs. So the inner product, x transpose xi, is just the total production cost of some production plan, right? So let's assume we would like to minimize the risk of the total production cost. And as a risk measure, I use here the first upper partial moment, which is basically this expression here, essentially it just evaluates the expected cost above a certain given threshold B, right? So now let's assume a very simple stochastic setting. Let's assume that the unit production costs, so all components of the vector xi, are independent and uniformly distributed from 0 to 1. So that's really the simplest continuous distribution you can think of, right? A uniform distribution from 0 to 1 in each component and independent. Turns out that in this case, already just evaluating the expected risk, the objective value of this problem, so the first lower upper partial moment, for a fixed decision is sharply hard. Okay? So that means that the CPU time of any known algorithm for solving that problem grows exponentially in the number of products. So grows exponentially in the dimension n of the vector x and the vector xi, right? And that's just evaluating the objective function. We haven't even optimized this yet. The reason for that is that we have to evaluate an integral. The expectation is an integral, and high-dimensional integrals are intractable. Okay? So people refer to this problem sometimes as the curse of dimensionality. The computational power that you need to solve a problem grows exponentially with the problem dimension, if you want to solve the problem exactly, which is what I'm assuming here. Okay? Now, this is the first shortcoming. The second shortcoming, in my opinion, is even more severe. And that is that actually the distribution P of the uncertain problem parameters is never observable in practice. Distribution is something we make up in our minds to build models, but it doesn't exist. Distribution always has to be estimated from limited data or has to be inferred from expert advice, and therefore it's always affected by estimation errors. It's never precisely known. So that means that a fundamental input of our optimization model is simply unknown. Now, this is a problem because it turns out that estimation errors in the inputs of an optimization problem, they carry over to the solution of the optimization problem. It's not surprising. That's simply a manifestation of the famous garbage in, garbage out phenomenon. Right? If your input is bad, of course, you shouldn't expect the optimization results to make any sense. So I would like to demonstrate to you this effect in a simple example. So let's assume that there are 10 different projects that you could carry out, that you could implement. So you're some manager, right? You have 10 different projects, but you cannot implement all of them because you have a limited budget. So out of these 10 projects, you can pick 5. Okay? Now, the blue bars here, they visualize the expected net present values of these 10 projects. Okay? So, given this information, which projects would you choose? This is a very simple question. Exactly. So you would choose the projects that have the highest expected net present value. In doing so, you will basically maximize the average of the net present values among those projects that you selected. Okay? Now, unfortunately, however, these expected net present values, they are not known to you, right? Because these are expectations. So in practice, you will always have estimation errors, and I could visualize the estimation errors, for example, by error bars. Now, just for the sake of argument, let's assume that for half of these projects, we've underestimated the expected net present value, and for the other half, we have overestimated the expected net present value. So let's assume that our estimates look like that. Okay? It's a bit exaggerated. These are huge errors, but just for the sake of argument. So this is not completely unreasonable because this means that on average, the estimation errors cancel out. Right? And this makes sense if you have a large number of projects, then sometimes you're lucky, sometimes you're unlucky, and errors should cancel out roughly. Now, a decision maker who doesn't see the true expected net present values, but only sees these estimates, such a decision maker will rank the projects in a different way. This decision maker will rank the projects like that. And then this decision maker will pick the 5 projects that have the highest estimated expected net present value. So we'll pick those. And now you see the problem. The problem is that those projects whose expected net present value has been overestimated are more likely, much more likely, to be selected than those whose expected net present value has been underestimated. And that means that the estimation errors across those projects that you select do no longer cancel out, but they're actually on average positive. So it means you're too optimistic about what you can achieve, right? So the red line here denotes the average of the estimated expected net present values of the projects that you selected. Now, of course, this is treacherous because this estimated average is not achievable in reality because this comes from the estimation errors. So if you look back at the true expected net present values of the projects we selected, right, they look like these blue bars here, and we take their average, then of course their average is below the gray line. It must be below the gray line because the gray line is the best you could do if you had full knowledge, which you don't have, right? So you need to have something that is less good. So the problem is that by using estimates instead of the real values, by solving an optimization problem, you will be too optimistic. You will overestimate the amount of money you can make. In reality, you will then be disappointed because the true mean of or the true quality of your solution is inferior to the best you could have done. The difference between what you think to get and what you actually get, so the difference between the red dashed line and the blue dashed line, is sometimes referred to as the post-decision disappointment. So the bottom line of this is that even if the input estimates are unbiased, so even if the errors cancel out in the inputs, the optimization results are biased. And they're actually biased in a bad way. You're too optimistic about what you can achieve, and you will be disappointed when you implement your decision. So some people refer to this phenomenon as the optimizer's curse. You're being too optimistic, right? Question? Yeah. So now, most likely I'm going to just throw this in somebody's face. Yeah, exactly. That is. Just wanted to make sure that everyone is awake, okay?
Sorry, my question relates to the fact that you said that the post-decision disappointment, if I was to do it completely randomly right now, I mean, I would still be disappointed, but then is there a measure of like how...
if you pick the projects randomly?
Yeah.
No, then actually in the limit of many projects, you would on average, the estimation error would cancel out, but you wouldn't be optimizing, right?
Yeah.
Of course, making a completely random decision is not an intelligent thing to do, so you shouldn't expect to do well. Okay. But it would be a decision that would not lead to this kind of disappointment. Okay. Yeah. Thank you. Okay. You can keep it, and maybe you throw it to somebody else later. Any other questions? Okay. So we have these two fundamental shortcomings. The curse of dimensionality. We cannot solve large problems exactly. And the optimizer's curse. If we use estimates naively as an input of an optimization problem, we will be disappointed. So now I would like to look in a more systematic way at optimization problems under uncertainty. We discussed that distributions are not observable in practice. But what you typically have is a bunch of data. You typically have samples from the distribution that is relevant for your optimization problem. So just to keep things simple, let's assume that we are given a bunch of capital N different samples of the distribution P that we don't know. Let's assume that these are all identically distributed, of course. They all follow the distribution P, and they're independent. Okay? So like in machine learning, I would like to refer to these data, to these samples as the training data, or the in-sample data. Right? So very abstractly, what we would like to do, we would like to find some procedure that takes this training data as an input and outputs a candidate decision x hat that is feasible in our optimization problem and hopefully near optimal. and also an object J hat, which I call a certificate, which is sort of a measure that quantifies how good our solution is. Abstractly, these two objects, the candidate decision X hat and the certificate J hat, they're just functions of the data. And the black box here contains some transformation that maps the data to a decision and a certificate. Okay? Now, of course, the question is, what should we put in the black box? But before we discuss this, let's maybe talk quickly about how we would actually know whether a procedure that we put in the black box is a good one or not. How do you measure the quality of a decision, right, that you inferred from historical data? Well, again, like in machine learning, what you ideally would do is maybe you have another set of data, which you call the test samples or the out-of-sample data. These are the red data points here. They're also independent and identically distributed. They follow the same distribution, right? But these samples, you put them aside. You didn't use them to compute your decision X hat, right? You put them aside. Once you have your decision X hat, you use these additional samples to evaluate how good your decision actually is, right? It's like, you compute the decision, and then you basically simulate how much money would I make if I had implemented this decision, and these would be the uncertainties that come along, right? So the quality of our decision X hat could then be approximated by the average cost of the decision X hat with respect to these different samples. So the m here is the number of test samples, and of course if the number m of test samples tends to infinity, then you have here an average of IID random variables, and this will converge to the expected value, okay? So if you have an infinite amount of test samples, that would be an ideal case, this quantity here would converge to the true expected loss of your decision X hat. Now this quantity there is important, and it's important to understand it correctly. It is an expected value, but the expectation is taken only with respect to this psi. You can think of this psi as a single test sample that is independent of the training samples. Now the decision X hat is uncertain because it is a function of the training samples. It depends on the green samples, right? But we're not taking an expectation over those. The expectation here is only taken with respect to this out-of-sample sample. Okay?
But are you assuming that the in-sample and out-of-sample data, they are following the same distribution?
We're assuming they're following the same distribution. This is already an ideal setting, because in reality you don't know whether, if you observe a time series, you can usually not be sure whether these are IID data. And of course statistics has methods of transforming time series so that you ideally get an IID sequence. Let's assume that we have a statistician that has done that for us already, okay? Because this is already difficult enough. Okay? So this expected value here I call the out-of-sample performance of my decision X hat. What is very important to remember is that this out-of-sample performance, even though it is an expected value, it is actually random. It is random because it depends on the decision X hat. The decision X hat depends on the training samples, and the training samples, they're basically random, right? Okay. Now, what can we, so this is actually the true objective value of our decision X hat in the optimization problem. And of course, this quantity needs to be small. We're happy if this quantity is small. Of course, our X hat was constructed as a feasible solution for the optimization problem. And therefore, the cost of that decision cannot be smaller than the optimal cost that you could achieve if you knew the distribution. So it's trivial that the out-of-sample performance is larger or equal to J star, the true optimal value of our problem that we don't know. That's a lower bound on the out-of-sample performance. But this is trivial, and it's not very informative. It doesn't help you. It doesn't say much, right? You're not really concerned about your costs being too low. The thing you're worried about is your costs being too high. So the thing you really want is an upper bound. Ideally, you would like an upper bound on your out-of-sample performance. So that's the goal in, say, data-driven optimization. You would like to establish, ideally, a finite sample guarantee, and that's a relation that looks a bit like that. So ideally, we would like to construct a certificate J hat as a function of the training samples in such a way such that we can guarantee that the out-of-sample performance of our decision X hat is small or equal to the certificate J hat with high probability 1 minus beta. You should think of beta here as a very small number. You can think of this as a significance level. So 1 minus beta would be a confidence level. And OK, so this inequality can either be true or not. That depends on the training samples, right? So the probability here is taken with respect to the n IID training samples. That's why I write the distribution p to the power n, right? That's p to the power n is actually the distribution of a sequence of n IID samples. Okay? So important distinction, right? The expectation here is taken with respect to this psi. The probability here is taken with respect to the training samples, which are implicitly in the candidate decision and the certificate. Okay? So that's the goal. I would like to put some method into the black box that gives me a candidate decision X hat and a certificate J hat that I can compute easily and that give me a finite sample guarantee. So if I have such a finite sample guarantee, then I know if I implement the decision X hat with a very high probability 1 minus beta, my expected cost if I implement my decision will be smaller or equal to this thing, which I can also compute at the beginning based only on the training samples. So that's something I know, right? So that's the guarantee that I have in advance before I implement the decision. Okay? Any questions about this? That's basically what we want to do. Okay. So what should we put? Oh, question. And the cube is behind you. Careful.
If you go back a slide, at the bottom PN, is that supposed to represent the training data as well? Or is that...
This one?
Is this a new set of endpoints that you were testing this on? Or this is the original training data?
That's the training data,
perfect.
right?
Okay.
This X hat, you should think of it as a function of these training samples.
Yep.
And this J hat, you should think of it also as a function of these training samples. I didn't tell you how these functions look like. That's what we're going to discuss now. But
that was just checking.
These are functions of the training samples, and we are taking the expectation, the probability with respect to those. Exactly.
Okay,
yeah.
Cheers.
Perfect. Any other questions? Okay. Everything crystal clear? What should we put into the black box? So what people have usually done in stochastic programming, they used the so-called sample average approximation to find solutions to optimization problems, to stochastic optimization problems. So basically, what you do here is, instead of minimizing the expected loss, which you can't because you don't know how to compute the true expectation, you just take your training samples and take the average of your loss over all training samples. That actually can be seen as an expectation as well. This is just the expectation with respect to a discrete distribution. And it's in particular the discrete distribution that assigns a probability of 1 over n to each of the training samples. Okay? That's the approximation. You approximate the unknown true distribution by this so-called empirical distribution, which just places probability 1 over n to each of the training samples. Then you minimize this average, this sample average of the cost across all x, and the optimal solution is, of course, a data-driven solution, right? So the optimization problem itself depends on the training samples. Clearly, then, the solution of this problem is a function of the training samples. Okay? That's one possible way how we can construct a candidate decision as a function of the training samples, by solving this thing. So x hat now is, okay, so the optimal solution of this sample average approximation problem. And this method has been very successful for various reasons. So first of all, it's very easy to solve this SAA problem, right? You can readily implement it. It's very easy to do it. What's nice about this, it comes with an out-of-sample guarantee, okay? So basically, what you can do is you can prove that the optimal solution of your SAA problem, the sample average approximation problem, is an epsilon suboptimal solution of the true problem, which you cannot solve, if the number of training samples is large enough. Okay? So people have proved, specifically Alex Shapira and Arkady Nemirovsky have proved that if the number of training samples exceeds an expression that looks like this, okay, then if you solve the SAA problem, the globally optimal solution of the SAA problem will be an epsilon suboptimal solution of the true problem with probability 1 minus beta. That's a very nice guarantee, right? So in order for this guarantee to hold, we need some assumptions. First of all, we need that the feasible set script x is bounded, so that the diameter of the set is finite. And we also need that the loss function is Lipschitz continuous in x uniformly across all xi. Okay, so these are some technical conditions that you need. But let's put that aside. The problem is that the number here, so the minimum required number of samples for a solution of a particular desired quality, can be very, very large. This is a nice theoretical result, but for it to be practically useful, the sample size n would have to be really, really large. Okay, so this would not be a problem if we knew the true distribution and we could just use a random number generator to generate an arbitrary number of samples. Okay? And actually that's what people in stochastic programming sometimes do. They assume they know the true distribution and they just randomly generate tons of samples. Then you can use this result very well. Okay? However, if you don't know the true distribution, which is what I'm assuming here, then the number of training samples that you have is fixed. These may just be historical observations. Maybe you have 10 years of data, then you have a certain number of, say, 12 times 120 monthly data points. You cannot just get an additional data point. You have to wait a month, right? And maybe you want to solve your problem before you waited for a month. And maybe 1 month is not enough. Maybe you need another 20 years. So we need another method. We need a method that can give us solutions of a guaranteed quality with a smaller number of samples. Okay? So let me demonstrate to you quickly what happens if we use this sample average approximation and we don't have enough data. Okay? So here's an experiment, and I apologize, it's a finance example, and it's just because this is the simplest example I could think of to make the point. So the details are not so important. The goal is here to solve a portfolio optimization problem. We have 10 different assets, and you decide today how to invest the amount of money that you have, your capital, into these 10 different assets, with the goal to minimize a combination of the expected portfolio loss plus the risk of the portfolio, which I quantify by using a conditional valued risk. The details are not important, okay? We have 10 assets, and I assume that the xi i's here, which are the returns of the different assets, follow some normal distribution that I construct in a particular way. Okay? So I make up the distribution. So that means I know the distribution. But I'm not going to tell the distribution to the optimization problem. So the optimization problem is like, faces a situation that a true investor would face in reality. It only sees samples that I generate from the distribution. Okay? The reason why I make up a distribution is because in the experiment I would like to generate lots of samples, and I can only do that if I know the true distribution. But I'm not going to tell it to the optimization problem. Okay? So it's fair. Now we assume that the investor that solves that problem has 30 training samples. So think of it as 30 months of stock price, monthly stock price data, and solves this mean risk portfolio optimization problem using the sample average approximation. Okay? Now, in order to get some statistically significant results, I repeat this same experiment where the investor sees 30 samples and solves the problem. I repeat this 10,000 times. Okay? And each time I record the optimal value of our optimization problem. Okay? The optimal value will be random because my samples, which are the input of the optimization problem, are random. So in the end, I get a histogram of optimal values of my problem. And that is the green histogram here. So first thing to observe is that this histogram is very much spread out. So there is a lot of uncertainty about the solution that you get, and that should already make you suspicious. Okay? It's not a good sign. You want to solve a problem that has a unique solution. If you get many, many different solutions, if you repeat the experiment, then probably something is fishy. The other thing is that actually I solved the problem also with the true distribution, which I know, right? And the optimal value, J star, would be here, the vertical dashed line. What you see is that the green histogram is mostly to the left of the dashed line. That means the SAA problem underestimates the risk of your portfolio. It's too optimistic. That's exactly the optimizer's curse that we discussed before. Okay? Now, each of these 10,000 times, I got an optimal portfolio from the SAA problem, an X hat, right? Which is it's a random portfolio. That depends on the training samples. So for each of these portfolios, I evaluated the true objective of the optimization problem by using another 10,000 test samples to compute the auto sample performance basically exactly. Okay? For each of the 10,000 optimal solutions, I do that, and I compute the auto sample performance in this way. And that gives me another histogram, and that's the red histogram. Okay? Now the red histogram is also, you see there is a lot of variance. So the amount, the risk that the investor will face in reality can differ a lot depending on the training samples, so depending on luck, essentially. The other thing, of course, out of sample, you can never do better. Your risk can never be smaller than the optimal risk that J star, right? Which you can only compute if you know the true distribution. So that's why the red histogram is entirely to the right of this black dashed line. Okay? So now, in summary, the green histogram, that's the in-sample performance of the portfolio problem. That's what the investor, when she solves the problem, thinks to get. Whereas the red histogram reflects what the investor will actually get. And there's a huge discrepancy between the two things. Huge discrepancy what you think you get and what you will actually get. And you see that you will be disappointed, right? So that's the optimizer's curse. Okay. So the SAA does not work well if you don't have enough samples. So I would like to propose now to put some other method into the black box, which is a method of what we call distributionally robust optimization. So here, we formulate an optimization problem that can be interpreted as a game between the decision maker and some fictitious adversary. And you can think of this adversary as nature. So what we actually do is we take our training samples and we use these training samples not to construct a single distribution that should approximate the unknown true distribution. Instead, we use our training samples to construct a whole family of different distributions that could explain the training samples that we see. Okay? So I denote this set of distributions by p hat, sometimes p hat n, to emphasize that it depends on the n training samples. And I will call this set the ambiguity set. The reason is that uncertainty in the distribution of a random variable is often termed ambiguity. Okay? So that's a family of distributions that all can explain our training data with sufficiently high confidence. So my distributional robust optimization problem is now a game where the decision maker first picks a decision X in order to minimize cost. After this decision has been chosen, your adversary, or nature, can pick a distribution Q inside the ambiguity set with the goal to inflict maximum damage. So with the goal to hurt the decision maker as much as possible, with the goal to maximize the expected loss. Okay? So that's a two-person zero-sum game between the decision maker and nature. So the optimal solution of this problem, I denote again by x hat, and of course this optimal solution is again a data-driven solution of our problem, because the optimization problem, or this minimax problem, is constructed from the training data. So if the problem depends on the data, clearly its solution must also be a function of the data. Okay? I use now the symbol J hat to denote the optimal value of this minimax, of this distributionally robust optimization problem. Okay? So that's a proposal. Now, of course, I need to tell you how we construct the ambiguity set, this family of distributions. And so I would like to construct a family of distributions that satisfies a number of properties. So I'm going to set up a sort of a wish list of properties that I would like this ambiguity set to satisfy. So my first wish is that the solution of this problem, the distributional robust optimization problem, should give me an out-of-sample performance guarantee of the type that we've seen before. So I would like to have a relation of this kind. Okay? Clear. I want that. Second thing, what I would like to have is also what I call an asymptotic guarantee. Imagine that you get a larger and larger amount of training samples. The number of training samples goes to infinity. If the number of training samples goes to infinity, then you can basically reconstruct the true distribution exactly. And in this case, you should be able to solve the true stochastic program exactly. So that means the solution of your distributional robust optimization problem, in the ideal case, should converge, with probability 1, say, to the solution of the true problem. Okay? Ideally, that's what you would like to see. And third of all, and that's maybe one of the most important things, all of this is useless unless you can actually compute the decision x hat efficiently. So you would like this distributional robust optimization problem not to be too difficult. Ideally, I think you would want it to be not much harder than the sample average approximation problem. Okay? Now that seems maybe to be a lot to ask, because this looks much more complicated. We don't only have one distribution, we have possibly infinitely many distributions in our ambiguity set. For each of these distributions, we have to calculate the expected loss for every possible distribution, then for every possible decision x, and then we have to maximize over these distributions and in the end minimize over x. So this seems like difficult. Okay?
And is x feasible for any distribution in the ambiguity set or not? I'm not talking about optimal feasibility. Is it feasible?
So because we look at one-stage stochastic programs, the way we define the problem here, we're only allowed to pick decisions x that are in the feasible set script x. So by construction, whatever comes out of this will be in script x and feasible in the true problem. Okay? Situation would change if the constraints depended themselves on the distribution. Say if we had chance constraints or expected value constraints. This would be a more general model that I would like not to discuss at this moment. So this would be harder. Yeah. Any other questions? Okay, so this is my wish list of desired properties. I would like to construct an ambiguity set such that the solution of my distributional robust optimization problem satisfies these three properties. So let's see whether we can do that. So the proposal is to construct this family of distributions basically as a ball in the space of all distributions. Now, of course, this is a complicated ball because distributions on, say, k-dimensional space or so, these are complicated objects. It could be the normal distribution or whatever, right? And so these are infinite dimensional objects, and we would like to look at the ball in the space of infinite dimensional distributions. So mathematically, I want to construct the ambiguity set in such a way such that every distribution Q in this ambiguity set lives on a set capital Xi. So this set is the support, or some people refer to it as the uncertainty set. We assume that we know that the true distribution lives on this set. Let me give you some examples. If the uncertain parameters reflect, say, demands for a particular product, then you know that the demand is always larger or equal to 0. So in this case, the uncertainty set, the capital Xi, would be the space of all vectors where each component is larger or equal to 0. So that's the non-negative orthant, right? You just know that the distribution needs to live on that set. If you don't know anything, this set Xi could also be the whole space, right? Okay? But sometimes, you know, some random variables, they live between 0 and 1. Maybe they're percentages, right? Many are non-negative. So this is exactly the kind of information that you pack into this set Xi. Okay, so every distribution in our ambiguity set should live on this set Xi, for which we know that the true distribution lives on it. The second condition is that the distance between the distribution Q and the empirical distribution should be smaller or equal to epsilon. The empirical distribution is the distribution here that places probability 1 over n on each of the training samples. So this is exactly the distribution that we used in the sample average approximation to approximate the unknown true distribution. Okay? So the 1 over n here, that's the weight, and this delta subscript Xi hat I, that's the Dirac point measure at point Xi hat I. So that's basically the distribution that puts all the probability mass at the point Xi hat I, right? And we take the sum of all those and divide by n. So that's, if you don't like the symbols, you can forget about them, right? It's just the distribution, the uniform distribution on all of these n different training samples. Given the data, that's maybe the best guess we have. We are pretty sure that the true distribution does not look like that. But it makes sense to assume that the true distribution is close to that distribution. Okay? And we say here it should be within a distance of epsilon. Epsilon is a prescribed tolerance. It's the radius of the ball. So you fix it as a decision maker. Okay? So now the most important thing is, how do we measure the distance between two distributions? Okay? It's not at all clear how you would do that. And what I'm proposing here is to use the so-called Wasserstein distance for distributions. So here is a definition of the Wasserstein metric, or Wasserstein distance, between two distributions, Q1 and Q2. So this distance is defined as a solution of an optimization problem over some test functions f. These functions f have a Lipschitz constants of smaller or equal to 1. What does it mean? It means that the slope of this function is always between +1 and -1. It cannot be too steep, right? So these are functions that are not too steep. What I do is, for any fixed test function f, I evaluated the expected value of f of xi with respect to the first distribution and with respect to the second distribution, and I take the difference. And I try to maximize this quantity over all test functions with this slope constraint. Okay? This is abstract. It's quite abstract, okay? So if you don't like this, you can basically forget about it, okay? It's just a way of defining the distance, okay? I'll give you another definition later, which is equivalent to that one, and I'll explain that one in more detail. So at the moment, just think of it as a way of measuring the distance between two distributions. Yeah. Okay. So that's the approach I would like to propose. We solve a distribution robust optimization problem with respect to an ambiguity set that is a Wasserstein ball. A ball in the space of distributions with respect to the Wasserstein metric. Okay, so now, and that's the whole of the rest of the morning, I would like to show to you that this choice of optimization model actually satisfies the 3 desired properties of our wish list. So it gives you an out-of-sample performance guarantee, it's asymptotically consistent, and that's maybe the surprising thing, you can solve that problem quite efficiently. Actually, what I'm going to show to you is that in some interesting cases, you can reformulate this complicated distribution robust optimization problem over Wasserstein ball, so where we optimize over a set of infinitely many infinite dimensional distributions, that this problem can be reformulated exactly as a linear program. Okay? Question?
Is it correct to say that the worst distribution always located in the border of the ball or not?
That's correct, because look at the inner problem here. Okay? The inner problem here, the problem that nature solves, it's a maximization problem over all distributions in some set. The set is a ball, so it's a convex set, right? And the objective function is an expectation. So that's basically an integral with respect to the distribution Q. But an integral is linear in the distribution. So the objective is linear, and the feasible set is convex. And you know that if you optimize a linear function over a convex set, then the optimum solution will always be at the boundary of the feasible set. So, yeah, and that's actually at the heart the reason in the end why we can solve this.
And perhaps the worst distribution is the one with the fat tail, right? Or not?
No, it will not have fat tails. We will see the worst case distribution. I will show it to you. Yeah. Okay? Right. So actually, we have the 3 properties of our wish list: finite-sample guarantee, asymptotic consistency, and tractability. The first 2, I don't want to spend too much time on them, because that's basically probability theory and statistics, and I'm not really an expert for that. So I'm just basically using results from the literature that I can use to get these results. And this workshop is all anyway about optimization. So I would like to focus on the 3rd thing, which is the tractability, which is the important thing, because we need to know how we can actually solve this thing, right? But let me quickly talk about the finite sample guarantee first. So it turns out that we can use a so-called measure concentration result from the probability theory literature to give us an out-of-sample guarantee for this Wasserstein distribution robust optimization approach. So basically, this theorem tells us that the empirical distribution, p hat n, so the uniform distribution on our n training samples, converges exponentially fast to the unknown true distribution with respect to the Wasserstein metric if the number of training samples tends to infinity. Okay? So a precise statement is shown here. The precise statement says the following. This distribution p hat n, the empirical distribution, is a random distribution because it's the uniform distribution of the training samples, and the training samples are random, right? So we want to know the distance between the true distribution that we don't know and our empirical distribution p hat n, which is random. And what we ask here, whether the true distribution is inside the ball of radius epsilon around the empirical distribution or not. So if this inequality, strict inequality holds, right, if this is satisfied, that means that the true distribution is actually outside of our Wasserstein ball. We want this probability to be small, okay? So what these people, Fournier and Guillain, prove is that this probability, which is taken with respect to the n training samples, right, this probability decays exponentially fast in the number of training samples n, and also in the radius epsilon of the Wasserstein ball. Okay? So if you want to make sure that the true distribution is inside your ball with high probability, there are 2 things you could do. The first one is you could increase the number of samples, and then the empirical distribution would move towards true distribution and inside the ball. But of course, that we can't do in reality because we just said that the number of training samples is finite. We cannot just, it may be very expensive to wait for a new sample. So that's not the right tuning parameter for us. The other thing we can do to guarantee that the empirical distribution is inside the ball is to inflate the ball, so make the radius bigger, okay? And that's the epsilon, okay? So now, of course, we don't want to make the ball too big, because if the ball is too big, then we include many, many distributions, and the worst case is too pessimistic. So we want this ball to be as small as possible, but we want to guarantee that with high confidence, the true distribution is inside the ball. So we basically can invert this formula here. So let's say we want that the true distribution is with high probability 1 minus beta inside the ball. That means we want that with very small probability beta, the true distribution is outside of the ball. So we would like the right-hand side here to be small or equal to beta. Now let's try to find the smallest radius epsilon for which this right-hand side is actually small or equal to beta. Okay? So don't look at the math. You don't need to read the details here, but you can invert this formula, right? So basically, you can, for a given number n of training samples, and for a given small significance level beta, you can compute the Wasserstein radius that looks like the formula here, which will guarantee that the true distribution is inside your ball with probability 1 minus beta. Okay? So there's a C here, which is a constant that is known to not depend on any of the problem parameters. And this constant has not been disclosed in the paper by Fournier and Guillain. Actually, we contacted them and asked them about the constant, and they said they didn't care about this constant. So they didn't want to compute it. They told us you can do it if you want, but then it turned out that this would be a very complicated calculation, and we think that nobody would give us credit for doing it. Okay. So we left it. Yeah. But of course, you're invited to compute that constant. So. Okay. So we've constructed the radius, epsilon n of beta, such that the true distribution P is inside the ball with probability or confidence 1 minus beta. That's what we did. Now, this gives us an out-of-sample guarantee, right? This gives us this guarantee. Okay. So the J hat, that's the optimal value of our distributional optimization problem. So that's the worst case expectation of the decision x hat. So that means it's the maximum of the expected costs over all distributions in the ball. Now, we know that the true distribution is inside the ball with probability 1 minus beta. So that means with this probability, the expectation under P is smaller or equal to the worst case expectation. So that means the optimal value of our distributional robust optimization problem gives us an upper bound that we can compute ex ante when we solve the problem based on the training data. We know this is an upper bound with probability 1 minus beta. Okay? Question. You need the cube.
I'm wondering about the tail of the empirical, the tail of P, right? We made the assumption that the tail of P decays exponentially. So
this result needs that the tail of the distribution P decays exponentially at some rate A. Okay, that's a technical condition. You cannot avoid that condition. Very often, I mean, if your true distribution was, say, a normal distribution or an exponential distribution, which are distributions that are frequently used, then this would be automatically satisfied. In many applications also, the uncertainty set is a bounded set. So the Xi set, you know your distribution lives on a bounded set. If you do know that, then of course, trivially, the tail is 0 as soon as you're outside of that set. Okay? Yeah. Any other questions? Okay, so we have a first sort of success. We see that this method gives you an out-of-sample guarantee that does not require you to scale the number of samples up. Okay? Second thing, and I don't want to talk much about this, you can prove that asymptotic consistency holds. So basically what you need to do is you need to set the Wasserstein radius to this epsilon n of beta. That's the formula from the previous slide. At the same time, you need to make the confidence that the true distribution is inside the ball. You need to make this confidence to converge to 1. So basically, the beta n, the confidence level, should also depend on the number of samples, and it should, this significance level, beta n, should become small exponentially fast in n. If you do that, so you set the beta n to something like that, you substitute it into the formula for the radius, and you solve your problem, then you can prove that the optimal value of the distribution robust optimization problem converges with probability 1 to the true optimal value of the optimal value of the true problem, and any cluster point of the optimal solutions of the distribution robust optimization problems converges with probability 1 to a solution of the true problem. Okay? The proof is complicated, and let's leave it, okay? Right. Any questions up to here? Okay. So now the main thing, and that's the tractability. I would like to show to you that this distribution robust optimization problem can actually be solved in interesting cases. So we can reduce this problem in interesting cases to a simple linear program or a simple convex optimization problem, which can solve by using standard solvers. So in order to do that, I need to give you an alternative definition of the Wasserstein metric. Okay? So you remember the first definition that I gave you, which I told you forget, is the one with that optimizes over the test functions. It turns out that, well, the original definition of the Wasserstein metric is an optimization problem. It actually turns out to be a linear program. And this linear program has a dual. And it turns out that the dual linear program looks like the one here. Okay? So that's basically a result due to Kantorovich and Rubinstein. They proved that the Wasserstein distance between two distributions Q1 and Q2 can also be expressed as the optimal value of a minimization problem. The minimization problem here runs over all distributions Q, and these are joint distributions of two copies of our vector of random variables, which I call xi1 and xi2. Right? So I have my vector of uncertain variables, and I copy it. Okay? So I get twice as many random variables. And, okay, I look at all distributions, all joint distributions of xi1 and xi2, with the property that the marginal distribution of xi1 is equal to q1, and the marginal distribution of xi2 is equal to q2. Okay? So we fix the marginals, but we look at all distributions with these marginals. So the dependence of the two distributions is free. And what we're minimizing is the expected value of the distance, so the norm, between xi1 and xi2. Okay? Now this is also a bit abstract, like the other one, okay? So let me explain this one a bit in more detail. So the problem here is that we look at situations where the set capital Xi of the uncertainty set is basically a continuous set. It could be the non-negative orthant or the whole space. And things become much easier if this set was discrete. Okay? So I would like to show to you what this definition looks like if we deal with a discrete set. And then you can easily imagine that the discrete set approximates a continuous set if just the number of discretization points goes to infinity in some way. Okay? So let's assume that our uncertainty set Xi is discrete and contains the points xi1 up to xi capital K. Okay? So I only look at distributions that live on these k different points, and that means each distribution is just a vector that assigns each of these points a probability that is non-negative, and the sum of the probabilities needs to be 1. So under this assumption that the uncertainty set is discrete, what does this optimization problem look like? The definition of the Wasserstein metric, okay? So let's write it down. Okay. So the distance between Q1 and Q2 can now be written as a minimum over distributions. I call them pi here, just okay? Bear with me. What I need to do is with respect to this distribution, I need to take the expected value of the distance between xi1 and xi2. Okay. So if the random variables are discrete, then the expected value just becomes a simple sum. Okay? That makes things much simpler. Now, the sum needs to go over all realizations of the first random variable, xi1, and the second one, xi2. Now, each of these can be one of these discretization points. Okay? So I need to sum over all k and l that go from 1 to k. I need to take the distance between xi k and xi l. And then I need to multiply this with the probability of these two outcomes, xi k and xi l, and that's just pi k l. Okay? So the pi, that's our distribution. And it assigns a probability to each pair of k and l. And the constraints are that the marginal distribution of the first xi needs to be equal to p. Actually, let me change the notation here. This will be a bit easier for afterwards, what I'm going to do afterwards. Sorry about that. So I'm deviating slightly from the slide. I would like to calculate the distance between two distributions q and p. Okay? I prefer to have fewer indices here, okay, when I write on the board. So pi is the joint distribution, and it needs to have marginals q and p. So the conditions can be written like that. The sum from L equals 1 to capital K of pi k L, that's equal to the distribution, the probability that the distribution P assigns to scenario L. And the other condition is that the sum from K equals 1 to capital K of pi k L needs to be equal to Q K. Okay, so that's the probability that the distribution Q assigns to scenario K. That needs to hold for every L, and that needs to hold for every K. Okay, so that here is the optimization problem that defines the Wasserstein metric in the case of discrete random variables. Now, this problem here has a very nice interpretation. This is just an optimal transportation problem. Okay? Think of these points here, xi1 to xik. Think of them as geographical locations. And assume that at each of these locations, we have a certain product, and there is a demand for that product and a supply for that product. So let's assume the distribution Q here, that's the distribution of the demand. So Qk, it's a non-negative number, that's the demand for the product in location K. P is the distribution of the supply. So assume that PL, that's the supply for the good at location L. Now what we would like to do is we would like to find first of all, the total demand is equal to the total supply, right? The total demand is the sum of the probabilities of the P, which is 1, and the total supply is the sum of the, total demand is the sum of the QKs, which is 1 because it's a probability distribution, right? And the total supply is the sum of the PLs, which is also 1. So in order to satisfy the demand in each location, we can ship goods from any location to any other location. And the amount of the good that we ship from location K to L, that's this pi KL, right? So I optimize over transportation plans. My joint distribution pi here is actually a transportation plan that tells me how many units of the product I ship from location K to location L. Okay? What's the cost of transporting 1 unit of the good from K to L? Well, that's just the distance between the two locations. That's this thing here, right? So the objective function is just the total transportation cost. Okay? So this is it's a simple linear program, a standard linear program, and it's a standard transportation problem. If you have had a course on linear programming, you've seen such a transportation problem with very high likelihood. Okay? The Wasserstein distance is nothing else than the solution of such a transportation problem. That's easy to imagine, right? So here is actually it's an animation. So you have the distribution Q1 and Q2. The distance between Q1 and Q2 is the minimum cost of moving the distribution Q1 to Q2, when the cost of moving a unit point mass from Xi1 to Xi2 is equal to the distance between the 2 points. So, if you transport it, it will look like that. That I computed from the solution of the transportation problem. Okay? So, the definition up here with distributions looks abstract. As soon as you formulate this as a transportation problem, it becomes easy. Right? So think of discrete distributions, think of transportation problems, and everything is fine. Any questions about this?
Yeah. I just want to make sure that I understand the indices correctly in the constraint of the linear program.
Yeah.
So
I made an error, yeah. No.
L1
It's from
to L, right? No.
made an error, yeah. Sorry.
Oh no, it's capital K.
yeah, this is
It's capital K above, but it's the definition of psi capital.
Sorry, which one?
No, you have capital K different points in your set capital psi.
So here I should sum over k, I suppose,
I
right?
think so, yeah.
And here over L.
Yeah.
That was the error. Sorry
Yeah,
about that.
exactly.
Yeah. Thanks a lot for paying attention. No, K. Yeah, both sums go to capital K. These are capital Ks, in case I didn't make that very clear. So I need two different indices to enumerate the scenarios for the demand and supply locations. But it's the same locations. Okay? Any other questions? Yeah.
So then in that case, this psi sub k and psi sub L that depend on the distribution, they are just assigned by the problem depending on the distributions that are being
They don't
evaluated.
depend on the distribution. They are given, right? They're given. The distribution is just the probability that you assign to each of these points, right? Okay. So like if you throw a die, then the xi's would be the numbers from 1 to 6, and the probabilities, the distribution is just, assigning a probability of 1 over 6 to each of the 6 outcomes. These are the outcomes. They're fixed. Yeah, they're fixed. We're optimizing here over the distribution pi. The distribution pi is the joint distribution, basically on a grid, right? Not sure. Did I answer your question?
That in that case, for example, if you're comparing these two distributions that we have here, Q1 and Q2, in that case, how do we, let's say, link this pi with the Qs that we have originally?
Like this, right? So the pi needs to satisfy these two conditions.
Okay, so this, what we have on the right-hand side of the equality, that's what we give to the problem, depending on the distribution, right?
So the decision variables here is the matrix pi with entries pi kl. These are the decision variables of this linear program. PL is the probability of scenario L under the distribution P. This is given. And QK is the probability of the scenario psi k under the distribution Q. These are given. The distances between the different scenarios are also given, right? All of this is a constant, this and this is a constant, and the pi's, they're the decision variables. Yeah? Yeah. So actually what I can do is I can put my discretization points on the horizontal axis here, and I can also put them on the vertical axis, so xi1 up to xi k, right? And basically you can think of PL as the distribution of these xi's. So you would give each of these scenarios a probability. It might look like that, right? Okay, so these would be the probabilities of these scenarios, and you could give all these scenarios on the vertical axis other probabilities, say something like that maybe. So this looks differently. And now what we're doing is we're looking at all combinations of these points in the grid, and we're trying to find the distribution on the grid points here. This is the pi, with the property such that if you sum up the probabilities along each vertical line, you get the probability of the corresponding scenario here under P. And if you sum the probabilities along each horizontal line, you get the probability of the corresponding scenario under this distribution Q. Right? That's the same thing. That's what these constraints do, right? This constraints here. So this here is a distribution PL. Say this here is scenario L, and this bar here reflects the distribution PL. This constraint says that this probability PL needs to be the same as the sum of the probabilities pi KL. The pi KL probabilities are the probabilities of these grid points all here, right? If we take the sum of those, we need to get that thing. If you take the sum of these probabilities, we get this probability. On the other hand, the other constraint here, this one, takes sums along the horizontal lines. So we fix some scenario psi k here that has probability qk, and this constraint says that this probability qk needs to be equal to the sum of the pi kLs over L along the horizontal line. Right? That's what marginal distributions are. Okay?
But
Yep.
how to fairly calculate the cardinality of K and L? How many K and L?
That's given. I fix it. I fix this, right? I fix these discretization points.
Yeah, I know it's given. But
Yeah.
the problem is that it's very sensitive, the number of K and L.
Absolutely.
Right?
Yeah. Let's assume this is given. What I'm going to do is I'm going to let, so K and L, the lowercase k and the lowercase l are just indices. The capital K, that's the number of points.
Yeah, the cardinalities.
And I will let that go to infinity. So in the end, what I would like to do is I would like to calculate this Wasserstein distance for distributions on a continuous set, say on a box, right? Say, yeah, on the unit box. So what I will do then, I will just add more and more discretization points inside this box until I almost fill the whole space. And without being mathematically rigorous, it will be quite clear what it will look like if this k goes to infinity. Yeah. Okay. Right. Any other questions?
So here it's a distance, so you don't really need to make any assumptions on the distribution functions of P and Q. But is it possible to deduce something if you have P and Q dependent from the computation of the distance?
So actually, you need some properties of the distributions P and Q. They need to have a finite mean. Because basically, we're taking the expectation here of psi1 minus the distance between psi1 and psi2, and you need to make sure that this is finite. And this will be finite if both the distributions P and Q have a finite mean. So that would be a condition. If you want to drop that condition, you could just assume that otherwise the distance between the two distributions is infinite, which would also be fine. Now, I didn't understand the part where you asked about when the distributions P and Q are dependent.
If P and Q are dependent, could you deduce?
You see, there is no notion of dependence as long as these are just the marginal distributions. The thing that makes them, well, they are distributions of two random vectors, right? They have the same size, these random vectors. Now what we do is when we introduce the pi, we introduce a joint distribution of the two random vectors such that both random vectors still have the same marginal distributions, P and Q. And the pi is what introduces a dependence, but it's not a dependence between the distributions, it's a dependence between the two copies of our random vector. And by solving the transportation problem, in a sense, we find an optimal dependence structure, right? our transportation plan pi determines the dependence structure. It comes out of the solution of this linear program. Okay, there's another question at the back.
Is that how you can create the metric of mutual information?
Mutual information is different. I think the mutual information involves some logarithms and so it will not, it cannot be expressed as a solution of a linear program. But you can use the mutual information as another, or the Kullback-Leibler divergence actually, is frequently used as a measure of distance between distributions. But it's not the one that we're using here. But this also leads to interesting, you could also use that one. This would lead to another class of distributionally robust optimization problems, but I'm not talking about those today. Okay?
So, the joint distribution, is it usually constructed in some way in practice? I'm just curious how nice the joint distribution usually is, because it can be something very degenerate, or it actually can be like a copula of the two marginals. So do you have any insights what actually happens in practice? How mathematically beautiful the joint distribution that's the solution of this problem is? Or it's solved without explicitly constructing it, and then you don't really know.
It depends on, you ask how beautiful, and of course that beauty is in the eye of the beholder. And it's also a question of when you think you have solved the problem, right? And now there is maybe a disagreement between mathematicians and computer scientists. So when does a mathematician think a problem is solved? Typically that is when they have made, say, an analytical solution, or say the more abstract mathematicians when they prove that there is a solution and it's unique or something like that. Computer scientists, on the other hand, is happy with thinks that the problem is solved if they have developed an algorithm that would compute the solution in polynomial time. Now here, this thing is a linear program, so we solve a transportation problem, and from the computer science point of view, you would say, okay, that's all I need. It's a linear program. That means I can efficiently compute the distance, at least between discrete distributions. For continuous distributions, it's a different question. If you would like to know the Wasserstein distance between two normal distributions, there is actually an elegant analytical formula for that. There may be some other cases, but the general case, when you have two general continuous distributions, you would have to solve this approximately. Turns out that we will not have to do that. We will not have to do that, but I will show that later.
I wanted to know, like, do you construct it explicitly, or is actually something else?
We will have to solve this problem implicitly when we solve the distributional robust optimization problem.
Thanks.
Any other questions? Okay, I think I've exhausted you enough. I think it's time for a break now, and we'll take up after how many? 15 minutes? Okay, good. Thank you.